All right, so thank you if you actually made it to the very last sessions of the day, and I very much appreciate you, not just going and actually trying to hear some other stuff, and thank you for your time.
Wait a minute, this isn't WhatsApp?
Yeah, I myself am trying to fight to stay with it, so I know that if you're in the audience, just, please just hang in there. So I'm also trying to work on my presentation style, so part of that is fighting back against PowerPoint, but the other part of that is the last few presentations I've done, I'm trying to show off some work that I've done, and when you do that, you get really excited and you want to just download on the audience and give them 80 million slides and tell them all this stuff that, they just glaze over. So I'm trying a different approach, trying to really, really reduce the number of slides that I have, really, really reduce the amount of information I'm trying to convey, and actually try to make it intelligible, and so that you won't, pass out of sleeping, while you're getting it. So in that thought, that narrative there, please ask questions at any time. And so hopefully I will be actually under time on purpose, and we can make it out of here, and you'll actually get something out of this. So the purpose of this talk is to get you to maybe think about some things in a way that maybe you have not before, or to ask some questions that maybe you haven't before, or just to see the world a little bit differently. So who am I? My name is Thomas Stover. I work now on supporting a mixture, code base that has a lot to do with native code, C, C++, and a heavy use of Erlang. And I came from a background of systems programming, primarily with C, primarily on Linux. And so my experience in the last 6-7 months has been trying to introduce myself to the universe of Erlang coming from that perspective. And that is a very interesting experience. And if anyone is coming from the other way around, I think it would actually even be harder. But that would be interesting if somebody would like to share that story with me or compare notes. And the only thing I'll say about that is I watched an excellent presentation about 3 years ago. And one of the main points that was being trying to convey was that this guy was so heartfelt with it. He says, don't stagnate. Don't let yourself stay in a comfort zone for 10, 20, 30 years, because even though that may be where you need to be and that may be what you're good at, you're still, your mind rots, your mind deteriorates. You actually get stupider the longer you stay comfortable with what you're doing. And so it is good to try to look at the world from a completely different point of view and to help to see what you can gain out of that. And when you lose that, you're not as clever as you think you are. If when you have that myopic vision, when you stay focused on just a little part of your little world, you're losing a lot, because the world is a wonderful big place with all kinds of stuff happening. So I work for this outfit called Alert Logic. And who are we? So part of the reasons why I'm here, obviously, is we are looking to find the best people in the world. We are in the cloud security space, and we are probably, in the private sector, we're probably one of the largest collection of Erlang engineers in North America. Yes. That's a really cool. We have some fascinating problem domain. We probably have one of the largest databases in the private sector. We have just some fascinating things. And like I said, we're heavy into native code as well, so there's a lot going on there. Okay, so moving forward here with our narrative. So there are a number of themes that are somewhat orthogonal, somewhat parallel, that all kind of come up for discussion when you're on a topic of sort of comparing and contrasting these two worlds. Two worlds being C native code and Erlang and Beam. And some of those we'll talk about more than others, but a few we'll just kind of touch on is the functional and declarative versus procedural imperative theme. That is fascinating, and that's an issue unto itself, but that's not really what we're talking about today. Real hardware versus virtual hardware is, or virtual machine, is something we'll touch on a little bit more, but again, that's not the focus. But it does matter. I continue to be dumbfounded by how the awareness level of people who don't seem to appreciate that for what it is. Not that either one is better than the other. They're both important concepts, but that's sort of faded away from discussion is more than I think it should be. Static versus dynamic typing. Not going to talk about that too much, other than to just mention that that is a big deal. I hate dynamic typing. Whatever, that's just one of those things you just swallow the pill, I think, with Erlang. Erlang people love it. That's great. It has its advantages, and that's cool, but just understand that it does matter. You are paying a price for that. And just, an analogy would be there is a Python project. I think it's Python, maybe somebody help me remember. And one of the things they just did, they modified the Python runtime in just a few ways. And one of the things they did was they just simply switched it to a static typing system. And they're getting orders of magnitude more performance. So the point is that you are paying a price for that. It does matter. And I think from the other way you're looking at it is from the, kind of relate to the last talk, from a static analysis perspective, that's the whole reason why we even have specs in Erlang is because, anyway, point is, I'll get off of that. Moving on, and then, but that does relate to the whole other reason why you have high-level tools in the first place, why you have things like Erlang and looking at things from a higher level perspective is the human performance versus computer performance. There's a trade-off. Not everything has to be done in assembly code. Not everything, we're not just soldering wires together, right? There's time to do all these things, and if you can solve problems using tools, appropriate tools that help the human performance to actually get something done, frequently that's much, much more valuable than how fast it's actually running on a computer. Okay, so the next kind of theme I'm going to call the layers quagmire. And so we can look at this in a few different ways of thinking of it. So one of the themes that's going on, I think, industry-wide and academic-wide is that you have these, if you look at, this is sort of a simplified view of contemporary computing. And one of the themes that you keep seeing is this replication of layers that do many sorts of the same things. It's kind of like the fractals in nature, or how the atom mirrors the universe, right? And so like if you take a higher level, what we see now is have these frameworks where we do cloud deployments, and we do where we take something, we generate something, we dynamically scale out, scale in, create images on the fly, destroy images, sort of thing. And as these systems advance, they take on attributes of operating systems themselves, and you're now at the point where we are writing programs specifically for these kinds of environments. So you continue, so you move on down, then we have where most of work is done today, the actual program that you do write to do something, right, supported by a user land. So like in a traditional operating system, that's going to be things like your C library, all the background daemons, your shell, and a thing like Erlang, right? That's your OTP framework. That's the actual Erlang shell that you've got to work with, and of course all this is on top of a number of other things. You've got your OS kernel today that can also be entirely replaced by a hypervisor directly. That's just dedicated to running other things. You can do now we have things like the Erlang on Xen, or Java on bare metal. There's a number of these other projects where you're just running that virtual machine directly on the hardware layer. And then you've got the other one that's getting a lot of talk now is this libOS concept, which would sort of be the native code equivalent of running, say, a VM on hardware. There's a number of examples like this. Let's say bare metal OS, I think, is a good one. There's the one that the Cray guys use. But basically the idea is that you're going to try to have a single tasking environment of some kind that is just to run some native code at the fastest performance that it could be. And then, of course, this is on top of all these other abstractions. And the reason I put part of this in here is that still a lot of people, and it's easy to understand why, but have missed the concept that what we think of as like CPU instructions is actually an API to an entire universe of software beneath that. So most of the things that are happening that we think of as hardware are very much in the domain of software. All the cache work, the branch prediction, the pipelining, there's a whole universe of software, and there are trade-offs for how much of that do we expose upwards to the programmers, to the users, and how much we keep internally, and a lot of that has just simply to do with legacy reasons, but it's just a fascinating thing to consider, that we just continue to replicate these layers over and over again. So, but more often than not, we think about the layers of, in a deployment context, of how is it that we are actually utilizing these things, how is it we're laying out these workloads. So, yeah, because of virtualization scheme. So hopefully, there's a few virtualization models I think we can just take a quick look at. Hopefully everyone's seen them before, but some of them have the trade-offs between efficiency and usefulness. Not everything is necessarily for performance reasons. It may just be for administrative overhead, for ease of just solving a problem, just simply having less hardware. But on the other hand, when you are actually trying to go for that performance curve and do the best you can with that, then some of these other things come back up. One of them, okay, we got you have a regular computer, an operating system, and you have a contain like LXC or a containerized environment, like Solaris container, something like that. Then you have the one that's probably the most common, where you have, you're like we're doing right here in this laptop. You've got computer, operating system, then we have virtualized operating environments inside of that. And on top of those, we have further operating systems with workloads, some of which inside of that we have virtual machines with workloads. So the point is that we're having overhead, 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 overhead. Sometimes that's a big deal, sometimes it's not. But at the very least, be conscious of it. It's amazing that we're not conscious of that. Most things now are you deploy in a cloud instance somewhere, and you're layers and layers and layers, all of which adds overhead. So part of reducing overhead is like we were talking about a minute ago, is you have these models where, okay, we'll just run a virtual machine directly on hardware, except the hardware to actually support different kinds of hardware is totally unrealistic at this point in history. So we just use sort of the hypervisor itself as our hardware abstraction layer, and then we target whatever emulated peripherals and stuff is inside that computer, and we can get a model like this. Again, we have a VM based and a native code based, but you do see that. And then this one I put in here. Most people probably never see this one, but this actually, in terms of the amount of dollars deployed and in terms of resources behind it, this one is huge. And well, I guess anyone know where you might see this? Well, let me explain what it is. So what you would have is you have a one or more nodes of a traditional operating system that's just basically running a front end, a batch scheduling is what it would amount to. And then you have an array of other computers that are simply running a single task per core, computing something. Sometimes that actually might be a VM, but it also could be native code. And that's actually, that's your cryptographic breaking technology. That's your guys who are, quote unquote simulating fission bomb, but actually, of course, it's to when we need to switch over and hack someone's key. But yeah, that's another topic. Okay, so the next theme, and that's kind of why the title of this talk altogether, is the concept of an operating system versus application operating system, or a microservice architecture, or different ways of looking at the same thing. So, what is that? What does that even mean? So an operating system at this point in time basically just means a resource multiplexer, just something that we're using so that we can run more than one program on the same computer. And the application operating system concept is we are going to take facilities and ideas that we would otherwise associate with this system, operating system, and sort of put that inside one little program. Excellent example being the Erlang system. And Erlang can be both of those, because of course you could make, and there has been, Erlang that is not the Erlang runtime itself is an operating system. And of course it also can mean something else entirely, which is the context of more than one compute node, and so you have a network operating system if you incorporate the distribution architecture as part of that. So a lot of different reasons why things contribute to why things are confused and why people have different perspectives, and why some people say, oh, it's an apple, it's an orange, it's a banana. Well, it's all of these things, just depending on what you're looking at. So when you're talking about the microservice architecture, generally what that means is that you have a message passing system of some kind. And so the textbook example of, what would a message passing microservice architecture be is a microkernel. And basically the idea is that if you were building a operating system kernel, you would divide that into these little bitty, services of some kind, and just implement some sort of minimalistic message passing, and just split the task it that way. Now, what's interesting is that although there are examples of this, this is kind of considered a failure. The presence of Linux itself being a monolithic kernel architecture, or sort of the opposite idea of that, is kind of, some would say put that argument to the side, but that's still, that does exist. It's still used in some ways, and may come back into favor someday. But a lot of the literature and a lot of the ideas from microservice architecture come from this. Okay, so wow. So like I said, coming to Erlang, a few months ago, new from the background, and when you learn that kind of stuff, you at least the way I did it, you do a lot of Google searches, you read different books, and you read different things, you look at examples, and there is so much confusion out there. And I'm not saying that I understand everything, but good Lord, the number one area where I think people are totally confused about is the process model. So let's take a minute to explore this. So in a traditional operating system, usually we've got a concept of processes that essentially means a protected memory space. What that means is that this is a facility given to us by the hardware itself, either for something like a memory management unit or a segmentation architecture, some kind of where it's implemented with protection rings, something to where we actually have a hardware-assisted process isolation. And we have a address space that is global amongst all the different things inside a process. And that's our process. A thread, in a traditional operating system sense of the word, is the same thing, except it shares that same process space. So we have intentionally given up a portion between 0 or 100% of that memory isolation between processes. And then there's this other concept, the most popular term for it being a fiber. There are other names for it. We'll use the word fiber. I like that one. Which is where you were either manually stack switching a frame, or you don't have a stack at all. An example of not having a stack at all would be the proto threads thing that you see in the Kentucky operating system. Manual stack switching would be like GNU, PTH, something like that. And the fiber concept does exist outside of Erlang. Yes, the Erlang process model lets us do these many hundreds of thousands of processes, and they're lightweight, and it's great, but that's not a unique thing. We can still do that with regular traditional native code. Rarely done, but it can be done. So, as I was alluding to, in the Erlang universe, our processes are implemented as a style of fiber. Okay. Why do we have the Erlang processes? This is an abstract concept. Why do we do that? There's a lot of reasons for that, a lot of different orthogonal reasons that paint this palette. And this is also contributing to confusion. One of them is simply we're trying to mitigate the drawbacks introduced with functional programming in the first place. Okay? What do I mean by that? So the functional programming model is we have a mutable state, we have immutable variables, and to pass state around we have to do tail recursive calls. But you get to the point where you can only do, if we're having to pass that as a parameter every single time, there's a limit to what you can do. So as a way of making that better, expanding upon that, we can move things into different processes. And that is a variation on the theme. So that to me, as I look at it, as I learn at it, that's one of the whole reasons why you have this multi-process model in the first place. The other one is that what's special about Erlang is that we're not just programming an application. You're programming a system at large. And in order to do that, you have to have the multi-process model. And then at the same time, that has given us a strategy for concurrency. So we can use that same strategy for expanding to multiple nodes or for SMP, but it works together. So you have this synergy between these three themes, and that's kind of the intersection of why you would have that is sort of why this comes up. I see a lot of confusion on that, but that's my take on it. I didn't write Erlang, someone else did, so maybe there's a better answer, but that's how I would choose to look at it. But I haven't seen it written down that way. I wish somebody would have explained that to me when I was first trying to read it. And I put 0 as another one there because, again, I don't know if this was an original design goal or not. And if you're fascinated with historical computing architectures, and who isn't, you have to bear in mind that especially in the 1980s, you had expensive production-grade hardware in use that did not support hardware-assisted memory protection or any kind of segmentation architecture. And the only way to do multiprocess in a protected way was to use a virtual machine and to make your own process model this way. As I understand, as I've been told, that was actually one of the original motivations behind some of the designs of Java, but I'm not an expert in that field. So, so does having these processes make anything faster in Erlang? We're told that a lot. So, well, it kind of depends. No, in some ways, right? So, hardware versus virtual machine. There's been, especially the last few years, right, when I think it was Microsoft Research was putting out a big kind of a publicity blitz about how you could do certain optimizations and with just-in-time compilers, and you could get various portions of interpreted code to run faster than optimized native code. And you actually had intelligent people with a straight face say that, well, now that means that VM technology is going to be faster than raw hardware. Well, no, perpetual motion is not real. You cannot take hardware, run simulated hardware that is faster than the hardware that it's running on in the first place. What that does simply mean, though, is that your optimization strategies can be superior, or that the original native code in the first place was just poorly written. That's a different concept, okay? Memory management, of course. So, yeah, you're paying a price for the convenience of not worrying about your own memory management. In terms of locality and when you can do garbage collection and some of these other things, but there are ways to mitigate that, and that may or may not matter, right? Again, it's a convenience. You have trade-offs. The dynamic types thing I talked about earlier. And sort of a big one, depending on what your problem domain is the no vector operations, meaning we don't have ways to do sort of SIMD or GPU acceleration, things like that. On the other hand, this is awesome. This is a really beautiful, powerful tool. I'm not knocking Erlang. I think it's awesome. It helps you out a lot, and just simply used appropriately in the right context or with the right use case, this helps you out a great deal. And in that sense, it is saving you time and performance. And then on top of that, as a distributed tool, you can certainly use that as a performance increase than you may have otherwise done. Okay, so security model. So that's another fascinating thing to me, is that, so when you come from systems, everything is based on, oh, okay, what is the security ramification of this, and what does that mean? And Erlang stuff, it's almost like, okay, well, we're just not even going to talk about that. So I'd like to kind of just fill in a little bit. So traditionally, when we talk about the security model for writing programs, right? The original concept was, you had a computer, it's locked in a room. If you have keys to the room where the guard lets you in the room, then you have access to the computer. So we call that restricted physical access. Now we still have that. We have the exact same thing. It's just simply restricted network access. So, and that's still used in some of the best, highest performing systems today, because you don't want to have overhead of SSL or something like that. You simply have a trusted network, and once you're behind a proxy, once you're behind a firewall, you are privileged enough to access such and such service, and you're in. So we still have that model. But most things, when you run locally on a computer, what the difference between the operating system processes gives you is a hardware-enforced memory protection to the point where you can implement a security, so you can actually set things up so that process A cannot read the memory of process B, this kind of concept. And then, of course, when you have more than one computer talking to each other, security is entirely based on, if it's not based on network access restriction, it's just based on cryptography, right? Okay. Now, as a note about that is, if you're doing this model of processes made out of fibers, like Erlang, because you're not using hardware for memory protection, the only way that you could actually make a security model that way would be through a VM technology, or something like the Google native code thing is fascinating, where the guys kind of sort of dynamically, sort of like a just-in-time compiler for already compiled code. So I think a way to look at, which I don't know that anybody else is describing it this way, but I would describe writing code for your Erlang VM similar to kernel programming, meaning that a few things. You are not, you are tracking, you are doing work on behalf of a user. So whereas in an operating system or in a system, you might actually allow that user to directly run code on your computer. And if you did that in Erlang, the analogy would be, hey, hand me a Beam compile module, I'll just run it. You could do that if you wanted to, but you're trusting them. So you're usually doing things like, I'm going to run this function, I'm going to facilitate this service, I'm going to run this process on behalf of some user. They have some kind of security context that's stored in a database or as part of our state, and that is what we'll use to enforce whether or not we'll let an action happen. And that's what's going on in a kernel. Same thing, so if the difference between user space and kernel space. And the other way you could think of that is in kernel space, if you have dynamically loaded modules, like say on Linux, and you let someone load a kernel module, you're doing just that very thing. You're allowing them privilege inside your world to do anything you want. And that's why there has to be a restricted access to something like that. Yeah, okay, so the other great, wonderful thing that the world of Erlang does for you, and in some cases, depending on what you're doing, the only reason to use it, or the primary reason to do it, is because the supervisory logic. So that you can, say, all right, we'll set up this sort of startup procedure, and this sort of advanced recovery procedure, and this sort of shutdown, graceful shutdown, this kind of thing. And that is lately, depending on how much you follow Linux world, that is kind of a front burner debate right now about kind of replacing the System 5 init script facility that you see with most likely looking like it's going to be System D, but there are others that may win out in the sort of natural selection of how software goes. Windows uses Software Control Manager, Service Control Manager, but they're the sort of systems level equivalent of those things. And so when you're trying to do something, say to run just on the Linux, and you have a complicated dependency procedure of what started in certain orders, you still have those same problems to solve. You just have to solve them other ways. And there's some elaborate, creative solutions that I've seen that do that, but they're not as graceful. And I have also read about systems where people use an Erlang Erlang Beam process that doesn't do anything except control the sequence that operating system processes are started in and monitors them, and it's sort of the watchdog for other things because it's so useful at that. Okay, so another area kind of compare the two would be when you're doing networking or distribution. So in the Erlang world, everything is boiled down to a message passing facility. If you're back inside the regular OS, you have sockets. You can still do sockets in Erlang, obviously. One thing people don't necessarily always understand about the sockets API that if you're using it as a higher level, is it's actually an abstraction to several different kinds of network protocols. So doesn't just have to be IPv4 or whatever. There is an API. So in that sense, it is a generic analogy. If you had to pick, what would be the equivalent of just one size fits all message passing for native code, it would have to be sockets. Then when you're inside the machine, native code, obviously you've got some more advanced IPC mechanisms, which are used internally by Erlang VM, but the point is that they still boil down to the same kinds of abstractions that you would have between both. I hear that clapping. Does that mean I'm close to time? Okay. Resource management is not necessarily something, it's kind of what I think of as a weak spot in Erlang. And by that I mean where you can sort of have tasks that are associated with credentials, that are associated with priorities or policies, or even accounted. So a lot of that stuff is still very much important to say, especially when we're trying to balance out different workloads on a cloud deployment, or just balance them out and which customer's paying more and things like that. It's an area for exploration. So is that a message on my, okay. This one's kind of neat. You've got the dynamic code, hot code loading Erlang. This still does exist in native code. You can still do this. I mean, it's done implemented in native code for Erlang, right? And the analogy would, usually what you do is there's a concept where you can dynamically load shared libraries or pieces of shared libraries. Okay. And you can, it takes more time, but you can still do that. Analogy is kernel modules. AIX kernel has a thing where you can load multiple simultaneous versions of a kernel module, and it's the exact same, concept that you use in Erlang, where once all of the users to the older code are finished and the older code goes away, what you don't have as well as you do in, say, POSIX Linux world, is the concept of your code being versioned on disk and in such a way that you can continue it, so you can indefinitely, persistently hold different versions of a library or a module at the same time. So I could just store version 1, 2, 3, 4 of the same library, and I can have multiple users of the same thing all working at the same time, all using it, and just that's how the system stays forever. I'm defeating myself. I'm almost running out of time, even though I was trying so hard to go through. So I thought you could, as a thought exercise, would be just kind of show a quick example of some where you might try to use native OS processes versus Erlang process stuff. And so we're going to be real hip and think about a bulletin board system. And there actually is a bulletin board system written in Erlang that I did find doing a Google search, but I don't speak Chinese, so I can't tell you anything about it. But that might be interesting if someone else knows about it. I'd love to hear about it. But let's say, let's just sort of like job interview style, whiteboard something out here. So let's say we had, okay, we're going to make this BBS system. It's going to have, multi-node support. We're going to want a security model with different users. We want to be able to run, external doors, and it's going to have a chat server. All right. So, if we're going to say, all right, let's just first look at like the total Erlang solution. I would say, okay, well, you're going to have to have some port drivers so that you can, talk to these external doors. That's how we'll do it that way. We can build us a chat server. That's great. That's Erlang. We can do that. We'll have our supervisory tree of some kind. We'll have a connection handler facility, and then so maybe we'll associate each logged in user with a process, a session handling process. Okay, so the connection handling thing is going to have some kind of user account database. It could get complicated. It could be done. There is a SSH server in Erlang. Okay, let's look at that if you just did straight OS processes. You can kind of keep the same thing, right? The door processes, we don't have to make a port driver. They'll just simply run they're all individual processes anyway. We can use IPC to talk with them. Chat server, still here. Instead of our supervisor tree, we'll have systemd. Instead of our connection handling, we'll just use SSH. And then you log in, and then maybe we make us, a custom shell or something that corresponds to this and talks to all this stuff. All right, so let's see, how did I do this? Yeah. So one thing about this, though, is we had this multi-node requirement. So I want to be able to expand this system to multiple users. So one way we could do this is just the naive approach is we'll have multiple deployments of this, and we'll do some sort of, DNS trick or something, round robin balance, or maybe a indirection layer in between, so that clients get connected to different SSH servers on different nodes. But let's say we want to make that a little more interesting. So what you would need is some kind of sort of session proxy facility that takes a logged in context, connects to another computer, which you would have other facilities, and then sort of somehow transcends that login credential to another box. We could build this, but that's a lot of work. So this, I think, is a good thought exercise as to where you could mix and match the two concepts. So right off the bat, I would use Erlang, I think, as a great way to do a communication mechanism between these things. Maybe make this whole session proxy concept out of Erlang. But yet your session handlers could still be operating system native processes, so you could still use the user accounts on the system. We could stick with SSHD, so we don't have to do anything. That's reliable, trusted code. Everyone's got their keys, everyone's got their passwords. We stick with that. On the other hand, chat server, why in the world do I not want to use Erlang for that, right? I like the Erlang supervisor stuff. And so we could mix and match, if we had, so we're like just a few minutes on time, but you get the idea. So that is it, and thank you for your attention. And if anyone has any questions, comments, anything, so appreciate it. Thank you very much. I've had a great time at this conference. This is the first time I've been here, and I've had a really good time. I'd like to thank, everyone that has helped participate, everyone that's helping to do everything they're doing and organizing. And these conferences are hard to put together. They're hard to do. I appreciate everyone sponsoring and everyone who has contributed to their time in some way of doing these things. They're fun to enjoy, but they are work to put on at every level, so I appreciate that from everybody. And I'd also say that the crowd here has been just really friendly. This is just I've been to other conferences of different, I'm not going to names and stuff. But you don't have that fun attitude. Yeah, people here are very conversational. They're very it's good. It's a good crowd. So feel good about your community.